Okay, so 23, we're on page 757 there. Okay, so we're going from n equals 1 to infinity. It's the typical. Negative 3 to the n minus 1 over 4 to the n. And the directions say determine whether the geometric series is convergent or divergent. It tells you it's a geometric series. If it tells you it's a geometric series, what I would do is what I call the rabbit method, because the book doesn't do it this way. I just start plugging in values and then find what your A is and find what your R value is. So if we plug in 1, I get negative 3 to the 0, which is 1. And then I get 4 to the 1, which is 4. Does that look right? Okay, and then the next term, when you plug in 2, you get negative 3 to the first over 16. And then when I plug in 3, I get negative 3 squared, which is 9 over 4 cubed. And I'm just going to write 4 cubed. I know it's 64, but you could even write this as 4 squared. When you're looking at this pattern, what are you noticing is it's getting multiplied by on top? Negative 3 on top, and it's getting multiplied by 4 on the bottom. You know, you could just leave this as 4 and 4 squared and 4 cubed. You'd see it's getting multiplied by 4. It's a little less mental math there, especially if the number is 17 or something where you feel like you need to multiply it out. You don't. So this is my what value? R. Okay? So if the absolute value of R is less than 1, what do we know? It's convergent. Is the absolute value of this less than 1? Yeah, so we know it's convergent. And I believe it says if it's convergent to find its sum, but that's the first part of that. Determine whether it's convergent or divergent. Yep, and then to find the sum of a geometric, you just do A over 1 minus R. So our A value is what? 1/4. Okay, it's just your first value. And then 1 minus, and be careful you use your R here, is negative 3/4. So we get 1/4 over 7/4, which is 1/4 times 4/7, which gives you 1/7. Does that seem right? I don't actually have the key in front of me, but hopefully it's right. Okay, I'm going to try this one similar to the way I did the last one, where I just start plugging in, and I'm going to see if it's a geometric. Sometimes it is, sometimes it isn't. So if I plug in 0, anything to the 0 power is going to be 1. Okay, plug in 1, and you get pi over 3. Plug in 2, and you get pi squared over, I'm just going to write 3 squared. Plug in 3, and you get pi cubed over 3 cubed. So what am I multiplying by each time? Pi over 3. Is the absolute value of R less than 1? No. Okay, so actually I should probably write this the other way then. So absolute value of R is greater than 1, because this is 3.14 over 3, and then we know it's got to be divergent. And then it's super quick, right?
I used the test for divergence.
Okay. Probably because the 43 looks like one where you do the partial fractions because of the denominator. The first thing I do when I see these, and I know they're telescoping ones, is I just start plugging in, because if all the middle stuff cancels and I don't have to do partial fractions, I wouldn't. I'm guessing we're going to have to. A lot of times I just plug in so I can wrap my brain around what's going on too. So here, if I start plugging in, I plug in 2 and I get 2 over 3. And then the next one, when I plug in 3, I get 2 over 8. It's not looking, usually when things are going to cancel, it's like a plus and a minus, and then the middle pieces are going to cancel. So I'm going to say that this is probably going to go nowhere. So I'm going to go ahead and switch this to 2 over n plus 1 and n minus 1. Have you tried any of that yet? Okay. So then we get 2 equals a times n minus 1, and then b times n plus 1. So if my n equals 1, then I'm left with 2 equals 2b. So b equals 1. And you might have your a and b in the opposite spots, but same thing. So I get negative 2a, right? So a is negative 1. So then I would switch these around here. And they probably replace this with like the I, because we're going to take the limit as n goes to infinity. I would say you're not going to have to be that technically accurate because they don't usually put these on the free response part. But for good practice, maybe you should, And remember, we're starting with 2 and going to infinity, so just be careful of that. Okay, and then I start plugging in. So if I plug in 2, I get 1 over 1. And then minus, plug in 2 and I get 1/3. They just might not cancel like they did in the notes. Okay, plug in 3 and I get 1 over 2. Make sure I don't mess up something simple here. And then plug in 3 and I get 1 over 4. So we might have to go further to actually see the pattern is what I'm thinking is going to happen here. That's fine. Yeah. And I might go a couple further so it's super easy to see for like everybody. So we got 2, 3, plug in 4, and I got 1 over 3 minus 1 over, I'm plugging in 4, so 5. I'll plug in 5, and I've got 1 over 4 minus 1 over 6. And then that's going to keep happening. My last term, maybe I'll do my last 2 terms here. That way I make sure I don't mess this up. So I'm going to go with the very last term. Remember, we're replacing this with an I, replacing that with an N. Let me just do that now so this is a little less confusing when I'm doing the last step here. So you'd replace these with I's, replace this with an N, and then we're going to take the limit as n goes to infinity. So my very last term, when I plug in n, will be exactly what was written there before I switched them to i's. And the one before that, what am I plugging in the term before that? What's the term before n? N minus 1, right? The term before it would be n minus 1. So we would have 1 over n minus 1 minus 1. So 1 over n minus 2. And then minus, and here we have 1 over n minus 1 plus 1, which will just be 1 over n. And then we're trying to get this to be like the telescoping where we can condense it down a lot. So the 1/3 here and the 1/3 here will cancel. And that pattern should continue. So this one here will cancel this one here. The one in the back will always get canceled with the one in the front. So when I get back to here, there's one in the back that's going to get canceled with this one in the front, right? And there's one in the back here that'll get canceled with this one in the front. And did anything else? Let's see here. 1/2. Like this one will end up getting canceled, right, with the next one in the front over here. This one will get canceled with the next one in the front here. So what's not getting canceled, I would say, would be this, this, and then the, opposite end of that, which would be this one and this one here. So that's what we're going to be left with at the end. And then what do I do with those pieces? Take the limit as n goes to infinity of that, which we can just leave it like this if we want to. The 1 plus a half will give me 3 halves. Or you can write 1 plus a half. It's up to you. And then we got minus 1 over n minus 1 over n plus 1, which is going to give me what as I go to infinity? 3 halves. So hopefully that's the answer. I'll double check it here. And sometimes you just have to list more things out to actually be able to see it a little bit better where they're canceling at. When we're looking at 41 here, what I would do is I would split that, and I would just do the 1 over e to the n and start with that piece. And then you can add that to this piece, right? And the piece back here, you might be tempted to be like, oh, I'm going to do test for divergence. So do it. You know, if you do test for divergence, we're taking the limit as n goes to infinity of this. And you divide everything by n squared, right? Wouldn't we get 0? What does the test for divergence tell us if it's equal to 0? It tells you nothing, okay? And that's where some people get confused. They go, oh, then it's got to be convergent. It doesn't necessarily have to be convergent. It just says if it doesn't equal 0, then it's for sure divergent, okay? So the test for divergence doesn't tell us anything there. So that was kind of a dead end for that piece. So we don't know that it's divergent just based off of that. Whoops. The first chunk here you can actually figure out just by doing, I believe, the rabbit method here. Let's try it. If I plug in 1, I get 1 over e. If I plug in 2, I get 1 over e squared. You see what I mean? 1 over e cubed. So what is my r value? 1 over e. That's like 1 over 2.7-ish. So is the absolute value of r less than 1? Yeah, so you can find your sum. I don't know if they're supposed to. Yeah, if it's convergent, find its sum. So let's find the sum of this chunk. So what goes in the numerator? 1 over e. And then in the denominator, we do 1 minus 1 over e. And now this might seem confusing, but it's not. You could also just do like where you multiply the top by e and multiply the bottom by e. That's probably the quickest way to find the sum of that. So the numerator just turns into 1, and the denominator turns into e minus 1. That's an answer. Okay, that's a sum. Now the other piece there, like I'm tempted to do partial fractions on it. I don't know that that's going to help me there. Let me think for a second here. Okay, so that other piece is like this piece, which we actually did in the notes down here, didn't we? What did we get for that sum? So you do it exactly like you did in the notes there. Didn't you get 1, I think, right? Okay, so that piece you could do just like the notes, and I'd encourage you just to do it, but that's got a sum of 1. So then your total sum is going to be this plus 1. Yeah. And I don't know if they keep it written like that or if they get a common denominator, but if you needed to get it to match, I would always try to get it to match the book. So if you're looking at the book answer, they got a common denominator that's equivalent to this. So you just do e minus 1 on top and e minus 1 on bottom. So you'd have e minus 1, and the top would be 1 plus e minus 1, which just turns into e over e minus 1. So those are equivalent.